I was just going through my flashcards and I thought that this actually made a very good example because it was related to something that I was discussing yesterday. When you're learning something and you come across a question and you can't answer it in the moment, a good strategy is just to tag it with the incremental everything tag and then just let it come up later. So this is a question I had when reading the Intro to Computation book, and I couldn't answer it on the spot because I don't think I had a good definition of computable and nor a good definition of undecidable. So I figured I'd just leave it and then come back to it later, and later is now. So let's, do the Socratic tutor prompt to get GPT to give me hints, but ultimately have me work it out rather than just get given the answer. So yeah, let me put up here, just copy the tutor prompt, create a new chat, paste it in here, and then I'll just copy the question in as well. Okay, cool. Think of a computable function. One thing is annoying is sometimes it will give you the answer to little subparts of it. So for example, it's told me that a decision problem can be seen as a special kind of function that answers a yes or no question based on the input. Kind of annoying. Yeah, but maybe I'll add that here. Decision problem. Output. Yes or no. It's just a yes or no question. And then, if you see, I'll probably need to clean this up to get rid of the this part. What I can do is actually use a portal in RemNote. I can move this to computability. Let's see theory. So now you can see it cleans up the hierarchy because this is now exists within computability theory rather than inside this rem. Kind of nice. So decision problem, and then computable algorithm. Maybe I'll just say computable. So when is something computable? All right, let's do the simplest things. Let's say one, a computable function adding two numbers. All right, let's say, what if the question was, is the output James's favorite number or something like that? It could require infinite computation because he might refuse to say. Let's come up with an undecidable problem that's more mathematical as opposed to about human preferences. Encryption and decryption both must be computable, even if they might take lots of time. it seems like the non-decidable part would be understanding the decrypted message, which is non-mathematical. Yeah, I don't know. I was hoping to get a different example because this one's pretty standard. How about this example? Let's say you have a function that returns a set of random numbers. The decision problem could be, will the function return the number 2 amongst those numbers? Okay. Well, I didn't really get an answer, but I did get an interesting nugget about the relationship to probability. So we made forward progress. So I can say like how it relates to probability. Or say how it differs from probability question. Definitive. Yes, no. All right, that'll do for now. Let's move on. It's basically like P be that's what I came up with yesterday. Just be the last index, the last edge, and the last node. Yep. E 2 0. Ordered. It allows repetitions, I think. Continuity. Okay, so I wanna edit this to make it shorter, but I'll answer this beforehand, otherwise I'll spoil the answer for myself. So the difference between an undirected graph and a directed graph. In an undirected graph, the tuples are not considered to be ordered, whereas in a directed graph they are. Then you have the arrow between them. So edit, yeah, and then if I want to edit the hierarchy stuff above, I can click here to add it into the portal and then into a set of edge tuples. Yeah. Okay. Incorrect because it assumes that every pair of nodes shares an edge, so it's directly connected instead of just having a path between them, which is a weaker string. Each E is a tuple of 2 nodes. Start connected to N. No, I decided the other day that I was actually right here. You apparently are allowed to. You can say Depends how you want to define it, apparently, according to ChatGPT. If if I say that the path is a set of edges, then you're allowed to use edges. It's fine. But if I say P equals V1, V2, etc., then I can't use the edges. I can only use the nodes. So I'm going to delete that. And I can untag this rem because I don't need to see this again in the context of an incremental rem. Because it contains a cycle. Okay, cool. There we go. So yesterday I said this morning I would remember to go through and fill out the rest of these. So that's what I'll do. Yeah, I feel like for some of these concepts, it's difficult to get motivated to study them. Like for the simple cycle, I don't know why I should care about simple cycle. So I think for now, I'll just remove it and move on to trees because I've heard of trees. I think it has more relevance to my life. Haven't added anything about degree. So yeah, a formal definition of the degree of a node would be useful. Let's do that. Okay, so the degree is the cardinality of a set. Yeah. Mm. Okay. So now it's easy, for example, to define a leaf. Now I have this definition. In this case, I'll probably just copy it. Probably say leaf. And say formal definition, edges. Just say this equals to 0. In plain English would be degree of 0. Oh no, sorry, degree of 1. Yeah. Very nice. Basically just the same thing. Definitions, theorems, and proofs. Let's do some more reading. Suppose you want to prove the statement that for every graph G, the sum of the degrees of all the nodes in G is an even number. I actually can't remember how to write that. Aha. Super I. I guess you have to start off with the simplest possible graph and then show it for more. But then surely, if that's allowed, then the sum of degrees would be 1. Okay, maybe that's right then, because it's suggesting down here, I don't want to scroll too far to get the answer, but it's suggesting that it might be a calculus example. So this might be it. A single node. Single node. So maybe okay, they're suggesting it's true. I seem to think it's false for some reason. For every graph G, the sum of... Oh, shit. What about a directed graph? Directed graph with a self-loop. Ah, damn it. Okay. All right, fine. Yeah, okay, fair enough. So it seems like the fundamental theorem is correct. So, um, it would be nice to have a formal proof. I feel like it would be a proof by induction. Like you start with either like an empty graph, if that's possible, or a graph with one node, and then you try and prove it for all n plus 1 or whatever. Graphs of size n plus 1. Yeah, that's more like it. Consider a graph with no edges. What can we say about the sum of degrees of all vertices in this case? Graph with no edges. With no edges, the sum of degrees is 0. 0 is an even number. All right? There we go. Assume that for a graph with k edges, the sum of the degrees of all vertices is even. If we add one more edge to this graph, this new edge will connect two vertices. So I need some way of saying, I think what I said before is pretty much true. Like, 1, 2, plus 2 equals even number. Nice. It's still not very like formal. There's way more steps in there, right? Like even this, the statement that an even number plus 2 equals an even number, I don't think I've proven that elsewhere in my collection yet. But I am quite satisfied that I was able to come up with the idea of doing it by induction. You know, starting with an empty graph and then for each additional, assuming you have k edges or whatever. I probably would have said nodes, but whatever. Yeah, that's pretty cool. Now we've done our first graph theory proof. So I could put this proof somewhere in here. I have a special template, I should say, a tag that you can apply to a rem in RemNote. And then it's like a template where you can pick the different parts that you want to fill out and create and turn them into flashcards. It's very useful for things that are quite formulaic, like proofs. I always want to have the same parts memorized. So like the steps, why it's interesting, who it was discovered by. Usually I just put the steps and maybe some intuition or something as well. Anyway, the steps is going to be a list card, so I go like that. So I could say induction of edges, pick case, no edges. Induction on the number of edges. Base case, we have no edges, so the degree equals 0. Suppose a graph with k edges is an even degree. Graph with k plus 1 edges also has even degree. So assume a graph with edges has even degree. Yeah, I'd say this is more informal than formal, to be honest, but that's fine for now. I'll probably ask Paul like how he would structure this. I'd be very curious. All right, I think that's good enough for today. See you in the next one.